So what you will learn in today's session? We will cover the gradient boosting machine for classification, and also we'll take a look at the unsupervised machine learning algorithms like k-means clustering and the hierarchical clustering. Next, we will take a look at the time series. Time series is also one of the important algorithm, using which we can do forecasting, and then we will continue with, if time permits, we will continue with the neural network. We'll continue with neural network. Okay. So, okay, we will get started with gradient boosting. What is boosting? How many of you remember boosting? What is boosting? What is bagging and what is boosting? What is the difference between these two? We already discussed about the bagging and boosting. First of all, what is bagging? What is bagging? Which algorithm is used in bagging? Random forest. We discussed about random forest. Bootstrap aggregation. Yes. What do you mean by bootstrap aggregation? So that is your bagging related algorithm is random forest. So why it builds multiple tree? Why it has to build multiple tree in the case of random forest? They'll ask you in the interview, okay, and why multiple trees are created in the case of random forest? Random forest falls under bagging to get high accuracy. So what do you mean by high accuracy? You mean to say when I create multiple trees, will that improve accuracy? Yes, we cannot go by a single decision tree, right? So if you go by a single decision tree, it's something like I gave an analogy, right? So if I want to buy a car, we consult many people, and then we'll see majority of the people's opinion, right? So we majority of them, if they prefer a specific brand, then we will go by that. Similarly, one decision tree is with one decision tree, it is predicted value. We cannot, we cannot go by that because single decision tree is prone to overfitting. To reduce the risk of overfitting, it combines models, right? Many decision trees are required. So these combined models or trees have better performance in terms of accuracy. Instead of relying on a single tree, if we combine multiple models or multiple trees in order to achieve the better performance. The random forest use a method called bagging, right? So as part of bagging, it combines many trees, decision trees, to create a group or ensemble. Ensemble is nothing but group. Bagging means simply combining in parallel. Okay, we can create the algorithm can create the trees in parallel when it comes to bagging. So what is boosting? Boosting means combining weak learners, in sequential to achieve a strong learner from many sequentially connected weak learners. When it comes to boosting, the weak learners are nothing but the decision tree. In the case of gradient boosted decision trees algorithm, the weak learners are nothing but the decision trees. So each tree attempts to minimize the errors of the previous tree. Trees in boosting are weak learners, but adding many trees in sequential and each focusing on the errors from previous one, making boosting a highly efficient and accurate model. This final model aggregates the result from each step and a strong learner is achieved. It combines, even in the case of boosting, it combines all these trees, decision trees. So unlike bagging, the boosting does not involve bootstrap sampling. You need to remember this important point. It is not doing bootstrap sampling. Every time a new tree is added, it fits on a modified version of the initial data set. Since the trees are added sequentially, boosting algorithms learn slowly. Maybe it is one of the flip side of the boosting because the learning time is slow here. But models that learn slowly perform better. You need to remember this one. So in this case, the final model aggregates the result from each step and a strong learner is achieved. Okay. So in the case of bootstrapping, in the case of boosting, a loss function is used to detect the residuals. In the case of regression, gradient boosted machine for regression, we discussed, right? So we have used the mean squared error, using which the model can, will predict the errors, right? The sequentially created models predict the errors, and when you add the errors with your base model, you will get the predicted value. That is what we discussed. When it comes to classification, it uses something called logarithmic laws, using which, right, that can be used for classification tasks, which were the logarithmic laws. Okay, to understand gradient boosting algorithm, all right, I'm going to use this data set. It is a Titanic data set. You can find it in the net. Even in the case of Kaggle, you can find the Titanic data set. This is a very popular one. So in this case, the P class, age, and fair, and gender. These are the the independent variables or input variables. And here the target variable is target attribute is survived, actual. Okay, here 0 says the people did not survive. 1 is people survived. Okay, here 1 denotes true, 0 denotes no. Here the objective is you want to predict the probability of survival. Okay, they were the people, who can survive. The whole idea of this data set is right. So we are going to predict the fate of the passengers on Titanic ship based on the features like age, the class. This is passenger class. Okay, it's a categorical variable. It has 1, 2, 3, and we have 6, the gender. With this independent variable, we are going to predict the fate of the passengers on the Titanic ship. So as a first step, what happens is it fits the gradient boosting algorithm. What it does, it fits the first model to this original data set. This is what your first model. So unlike the gradient boosting for regression, it is not doing the average on your target variable. In our case, the target variable is survive. Instead, what it does is it takes the log odds of your target feature. So what do you mean by log odds? As part of logistic regression, we discussed what is log odds? Log of probability of success divided by probability of failure. So here, the true values. Usually, this is usually the number of true values, right? The success number of true values divided by the number of false values. The ones are trues and zeros are false here. So 4 ones and 2 zeros. Log of 4 over 2, we get 0.7. Okay, here we have 4 true values and the 2 false values are there in our target. If you plug this in our formula, log of 4 by 2, we get it, which is 0.7. It is the first estimation of our target survived attribute. So for this is the first estimation, predicted value, 0.7. So in this case, we have taken the log odds on this target variable, we get 0.7. In this case, what happens is for each and every observation, the predicted value is 0.7. If I create another column, predicted, this actual and predicted, here you will have 0.7, 0.7, 0.7, something. Look here, 0.7, 0.7, 0.7. And if you subtract the actual from the, predicted from actual, you get negative 0.7. Similarly, if you subtract this one, you get this value, right? So you need to subtract the predicted from your actual. If you do that, you will get the residual. So we can also convert this log odds ratio into probability. So probability of surviving is equal to, if you plug in this value 0.7, e raised to the power 0.7 divided by 1 plus e raised to the power 0.7, we get 0.668. If you round it off with 2 decimal value, 0.67 or so, you'll get it. If you, if you round it off, and almost it is close to 0.7. Okay, we have considered some of the assumptions like 0 point as the 0.5 as the threshold for classifying the yes condition and no condition. So what it says is, those customers or those passengers predicted with 0 point above 0.5, they are considered as 0.5 and above is considered as the survivors, and less than 0.5 is considered as they're non-survivors. Do you remember the threshold? Why we need to define threshold? I discussed in detail as part of the logistic regression. This is very important. Now, if you look at this one here on the right side, the chart here, the light circle, light blue colored circle and dark blue colored circles. or the observed values, the actual values, the survivor, right? So here, the dark blue dots are the passengers who did not survive, and the light blue dots are the passenger who survived with the probability of 1. Here, the dotted line tells us the predicted probability, which is 0.7. That is what we have seen it here, right? So now we need to find the residual. That's what we did it here. When you subtract the predicted between the actual, you get the residual. So obviously, the next step is a new model will be created for the same independent variables. Now the dependent variable is survived. Sorry, the residual, not the survived. Why the dependent variable is residual? The error, because the second model needs to predict the error. Okay. Please, in this case, you need to note down this one. We are restricting the number of leaves we will allow in the tree. Okay, exactly as we did when we used gradient boost for regression. So, but to make our understanding simple, I have limited the number of leaves to 3. But we can, the common practice is you can allow anywhere from 8 to 32, the number of leaves. Okay. Because of the limit on the leaves, what happens here, the residuals or more than one residuals landing into each leaf. For example, if the passenger class is not equal to 2, then it will come here. Age is greater than 30. If it is true, greater than 30, how many of them are there? Only 2 people are there. So 2 passengers, 38 and 35. Their residual is 0.3, 0.3. These two values land into a single leaf. And similarly, age is less than 30. That one lands into this one. So in this case, 3 passengers are falling in this category criteria. So here, 3 residuals are there for these 3 passengers. Okay, here the predictions are in terms of log odds. Which one? This is in terms of log odds. But the leaves are derived from probability, right? This is in log odds, the predicted value, whereas the leaves, it tells us probability in terms of probability. So we need to, convert this into common value, right? So in the sense, log odds, we need to convert this to log odds. So we need to compute or calculate the output for each leaf node. We need to use some formula for, we have some formula available. This is the formula. Okay, sum of residual divided by previous probability into 1 minus previous probability. If you plug in this value, the leaf value here, the first leaf if you take here, the residual is 0.3 divided by, because here we have only one value is there, we don't have to add them, we don't have to sum. This sigma tells us sum, but here there is no need to sum it, because only one value is there, divided by the previous probability into 1 minus previous probability. What is the previous probability? This is a 0.7, right? So 1 minus 0.7 into 1 minus 0.7, we get 1.43. That is the output for this leaf. Look here. And then the next one is 0.3 and 0.3. If you use the same formula here, so 0.3 plus 0.3, look here, divided by previous probability, sum of, right? In sum in the sense, for each observation, you need to do this one. 0.7 into 1 minus 0. Plus 0.7, we get 4.29. That is the output for this one. Similarly, if you do it, for this, if you plug in the value, so in the denominator you will get, you need to do it 3 times. And the numerator, it is going to be negative 0.7 plus negative 0.7, 0.03. You get if you plug in all the things, you will get, finally you will get negative 1.46. So why we need to use this transformation? Why do we need to use this formula to convert this as a log odds? Because the prediction are in terms of the log odds. The predicted value, you remember in the base model, the predicted value log odd of in the log odds, 0.7 log odds. But the leaf is derived from the probability, so we cannot simply add them together. Okay, to get a new log of the odds prediction without some sort of transformation like this. For that purpose, we are using this one. Very simple one. Okay, and now we got the predicted error available in terms of log odds. What is the next step? Next step is you need to add the base model predicted value with the second model's predicted error, but we cannot add them directly. Instead, we use the learning rate, like how I used the learning rate as 0.1 in the case of gradient boosting for regression. Similarly, we can use some learning rate. Look here, this is the, to get the predicted value, we need to add the first model's predicted value. Okay, and then the second model's predicted residual value. But this predicted residual should be multiplied with your learning rate. Got it? So in this case, what I'm doing is, instead of using 0.1, I have used 0.8 learning rate. Okay, so when you plug in the values, what will happen? So what is the output of this one? This leaf 1.43, 1.46, right? So here what we do is, I just took only one record here, one or two records. If I do it for each and every record, you will get confused. So here I have taken this one. So age is greater than 30. These two guys, 38 and 35. So what happens here, 0.7 is my base log odds. Remember the first model, we took the log odds on the actual, the survived, right? So we got a 0.7 log odds plus the learning rate is 0.8 into the 4.29, this log odds, which gives me 4.132 log odds. So in this case, we found out the log of the odds prediction. It is not, the probability. Okay, log of the odds prediction we found out. So now we need to convert the new log odds prediction into probability. So how do we find out? You have this equation, right? So e to the power, okay, actually, if you do this one, right, 4.132, e raised to the power 4.132, the log odds divided by 1 plus e raised to the power 4.132. You remember, so, any value divided by the same value plus 1 will help us to transform the values anywhere between 0 and 1, right? We are getting 0.805. So in this case, the passenger 38, the chances of survival is 0.80. The probability of survival is 0.805. Now we have the new predicted value in terms of probability. If you subtract this from your actual value, now my residual got reduced 0.19. What was the previous residual? 0.3. Now it got reduced to 0.19. Similarly, when the algorithm creates one more tree, what will happen is, look here, let us see. These are the first two trees. Look here, the base model and the previously we have seen, right, the weak learner. With these two things combined together, we got 0.805. In the third model, now it is going to, since we have the new predicted value, with this predicted value, we can compute the residual. So 0.805 minus this one, we get new is 0.19. Look here, this one goes to the residual, the leaf. And similarly, this one, if you do the 0.35, this goes this one. And again, I did not do this one for the sake of simplifying your understanding. I don't want to use so many values, you will get confused. So now for these two records, what is the predicted value? This is the one. Probability. We need to use that same transformation, sum of residual divided by the previous probability into 1 minus previous probability. When you use that, you will get the log odds ratio, new log odds ratio for this leaf. The output for this leaf, you get it. Now what you need to do is you need to add the base model's predicted value to get the predicted value for this one, right? For this third model, you need to add the first model's base model's predicted value plus the second model's learning rate into that residual, predicted residual, plus the third model's learning rate into residual. So that's what base log odds for this one. I meant about this one. And then for this one, learning rate into predicted residual value and learning rate into predicted residual value. If you do this, what will happen? New prediction for passenger class 1. Class 1, this one, right? 0.7 is the base model, and in plus 0.8 is the learning rate into the 4.29. That was the log odds ratio for this passenger, the predicted error, plus this model's 0.8 the learning rate plus 1.428. This one I'm talking about 1.428. If you do this, we get 5.24 log odds ratio. If you plug this into our the equation, right? So e to the e raised to the power 5.274 divided by 1 plus e raised to the power 5.274, we get 0.840. So in this case, the person with age 38, the survival, the probability to survive is 0.84. Now we can see that with this third model, the predicted accuracy increased, right? So here initially it was 0.805, right? So previously 0.7 and 0.805 and 0.84. So gradually the accuracy increasing it. Obviously the residual is also getting reduced. Okay, with this, we are able to understand this final model, right? By combining all these things, I'm talking about final model, the combination of these three aggregates the results from each step, and a strong learner is achieved. With this combination of three, the strong learner is achieved. That is what so now we have see in this case with three models, this is what we are getting it. Now, if we keep repeat the same process over and over again by building new tree, making predictions and calculating residuals at each iteration. I'm talking about this one iteration, this two iteration. With each iteration, when you do the same thing again, right? So we do it, right? So we do this. How long we do this? We do this till the residuals are small, super small, or we reach the maximum number of iterations. Okay, we set for our algorithm. Okay, so with this, I hope you guys are able to understand. It started with the base model. Okay, and iteratively created the weak learners in sequence, and each iteration we could see that the residual values are dropping. Look here, the residual value. This is the residual 0.3 to 0.9. From 0.19, it got dropped to 0.16. We could see that each iteration, we could see that the residual values are dropping. It is all possible because of combining all the weak learners that resulted in a strong model. In the sense, right, we could see a reduction in residual. This is how the gradient boosted tree for classification works. Got it. So now you understood, how the boosting, why the accuracy with boosting is better than the random forest and other algorithm. Here, each and every tree is trying to fix the errors generated by the previous tree, right? So that is the reason why we could see, better accuracy here.